I just want to double check. I am going to get screen sharing powers at some point, right?
Oh yeah, we should do that.
I mean, I can just, give my talk without the slides, but it's going to be really hard to explain all of those graphs in words only.
Yeah, let's do that. Well, actually, you already had it, I think. Just try to share for a second.
Looks like I can, so I will hang on just a moment and then throw all of that up there.
Jason, are you giving the introduction, I assume?
Yes, I have the Post-it note.
Okay.
But it's tiny, tiny writing. It will be a long introduction.
Somebody is asking where the recordings are going to be posted. And yes, we are recording this, and all the talks will be posted and linked from our physics seminar webpage. So I guess let me just find that link and post it in the chat. And there's recordings, not always video, but some form of recording available for talks from previous semesters as well. So that's the website with a full schedule of talks for this semester, and it is going to have the 2 videos, and you can get from there to other semesters as well. I see the number of participants is still growing slowly, but it is after 2, so why don't you go ahead, Jason?
You want to go ahead and start sharing, Lynn? All right, well, welcome to the Physics Seminar Series. Today on September 30th. Our series is, of course, supported by the Eddie and April Lucas Fund. And the speaker that we have today is our very own Lynn Buckley. Lynn graduated from Garden City High School just a little bit ago. Brand new student, came to WSU as an aerospace engineer and had the wonderful opportunity of taking physics from Elizabeth Berriman and myself. So a conversion happened to physics. Lynn graduated with a bachelor's degree in physics in 2019 and was the Honors College Student of the Year when they graduated, and has been the Shaw Summer Fellowship, held the Shaw Summer Fellowship in 2019 and 2020. One of the requirements to hold the fellowship in the summer is to give a seminar. And so as part of that requirement, this is Lynn's basically what they did over the summer during COVID. So this will be more interesting than usual. Lynn, of course, is a candidate for a master's degree here in the physics department. And so let's welcome Lynn, and we'll see what happens with modeling. Go ahead.
Thank you for that introduction, Dr. Ferguson. So today we're going to talk about stellar modeling. and what it means to use on-the-fly opacity calculations in stellar modeling. But before we get there, I want to start with kind of a big question. And that question is, how do we study the stars? So my hope is that you all have had an experience to get out and look at a properly dark night sky and see all of the stars shining down on you. And to me, that asks the question, well, what's up there? How do we know what we know about the stars? And studying stars can actually be a little bit difficult because they're far away and they're really big. So we are probably never going to be able to travel to a star to study it up close. We're certainly never going to be able to fit it into a laboratory. So what we have to do is use the observations that we can make. And when we're talking about stars, for the most part, we're talking about observations of the light that comes to us from the stars. In the last couple of years, we've been able to use gravitational waves to study objects in space, but those tend to be really massive objects, things like neutron stars and black holes. So when we're talking about, your more standard glowing stars that you see in the night sky, we're really restricted to the light that comes to Earth from them. But we can learn a surprising amount from starlight. So there's kind of two main things that we can get from starlight. The first is, how bright is the star? And by this, we mean not just how bright does it appear to us here on the Earth, but how bright is the star actually, taking into account how far that light has had to travel to reach us. And in astrophysics, what that is the absolute magnitude or the luminosity. They are both measures of the same thing, but on slightly different scales. So we can figure out how bright a star is that we see, figure out through a variety of means of how far away it is, and know how bright that star actually is. The other piece of information that we can get from the light of a star is, what color is the star? You can see this if you're fortunate enough to be able to walk outside and see the constellation Orion. Betelgeuse is a far redder star than the other brightest star in that constellation. And if we take our knowledge of physics and our knowledge of color and light, we know that the color of the star is related to the temperature of the star. So we have these two observations, how bright the star is and what temperatures / what color is it. So we can go ahead and make a diagram. These are Hertzsprung-Russell or HR diagrams, and they're really important to studying stars. And you'll see on this diagram that it's not a random distribution. We don't have all colors at all different brightnesses. We have a couple of main trends. So we can go ahead and somewhat creatively name these different sections. This portion here in the middle, where we have this big, long yellow streak, is the area where most stars are. That yellow on the diagram tells us there's a high number of stars that are at those values. And because most stars lie on that sequence, we can go ahead and creatively name it the main sequence. But there are also kind of two other branches that show up on the HR diagram. The one towards the top is the giant branch, giant again, because we are creative and really bright stars are really big, so they are giants. And then down here at the bottom, we have stars that are cooler and smaller. Cooler gives us the white, because the light from them is, white compared to most stars. And then the dwarfs because they are small. All of the data in this plot is real observational data that comes from the Gaia mission out of the European Space Agency. And so this is kind of one of the best observational HR diagrams we have of stars in the night sky. And we can learn a lot of information from HR diagrams, but in some ways, they prompt more questions than they answer. So two of these questions that might be important are, why do the stars end up where they are? Why are they concentrated along the main sequence? And then we have these two other branches, giants and white dwarfs. And then the other question is, how do stars change over time? Because each point on that HR diagram is, of course, the star at the point in time or over the points in time where it was measured. And so while we can understand how the night sky is right now, that doesn't tell us very much about how the night sky was, far in the past or how it will be far in the future. And so instead, we have to do something a little bit different to answer our question, we have to use some math. These are the equations of stellar structure. There's a couple of them, so we're going to walk through what each one does in a brief overview. So first of all, we have the equation of hydrostatic equilibrium. And this tells us that gravity, which wants to pull all the material of the star into the center, is counteracted by some pressure, whether that's gas pressure or radiation. So pressure. In this equation, we've got our capital P, which is our pressure, capital G, our gravitational constant. M of R tells us the mass at that given point in the star, and rho of R is the density at that given point in the star. So in this case, R tells us where we are, going from the center of the star all the way out to the far edge. So we know that the pressures are balanced. Next equation is our equation of mass continuity, which just lets us connect the density of the material at any given point in the star to the mass that's present. Fairly straightforward. Now we have to ask the question, well, the star is glowing. That's coming from something. So how do we connect luminosity, this capital L here, to the composition or the density of the star, the conditions that are there? And then the epsilon is our rate of energy generation. So whatever process is happening in the star that's generating that energy generates it at a certain rate. And we can use that to tell us how bright the star is going to be. Next question we have is, well, how does energy move around in the star? And there's kind of three main ways that energy can move around. We have conduction, convection, and radiation. Because stars are gaseous, we tend to ignore conduction and focus just on convection and radiation. So the equation for convective energy transport is how we relate temperature and pressure to the material around them. So the adiabatic index, that gamma there, is a property of the material. And this equation describes what happens if you have, blobs of gas of different temperatures moving around each other. The last official equation of stellar structure is the equation of radiative energy transport. This one's going to be important for the talk. And it describes how photons carry energy through the material of the star. So in here, we've got some constants out front, including our Stefan-Boltzmann constant there in the denominator. We've got, as we've seen before, density is our rho, luminosity is our L, and temperatures are T. But we also have this kappa value here. That is the opacity. It's going to become important a little bit later, so not to spoil anything for you. So we have these equations of stellar structure. We need one more equation that's not as neat to write down, which is an equation of state that kind of relates all of the properties of the material to each other. For the most part, we can treat stars as ideal gases. So that's typically what gets used with different corrections depending on how accurate you need your model to be. And then the other thing that you will notice in here is that none of these equations explicitly depend on time. And so if we want to model a star as it evolves over time, we need not just an understanding of how to solve all of these equations, but also an understanding of how the processes that are occurring change over time. You may have noticed that this ends up being a little bit difficult to do. And we are well past the point where we want to try and solve this problem by hand. For the most part, can't even really solve it analytically. So instead, we will turn to computer programs. The stellar modeling program that I used this summer is MESA, Modules for Experiments in Stellar Astrophysics. And we can use that. It's essentially a really fancy differential equation solver to solve the equations that we saw before. And we can combine everything together, make nice, lovely models, and turn it into a movie. So what we have here is an HR diagram, just like we were looking at before. We've got temperature down on the bottom, luminosity going up the sides, and we can watch how the star, which is this red dot, moves around the HR diagram over time. So that goes kind of quick, and we're already through the main sequence and up onto the giant branch. And if we wait until the end, we get some really interesting stuff as the star reaches the horizontal asymptotic giant branch. And if we were to keep this movie running, we would see the star float on down to the white dwarf branch. This star is a star like our sun, so it has a similar composition to the sun and the same mass. So if we take that last slide there, and we, there we go. We compare it to the HR diagram we were looking at before. These are on different scales, so it might be a little bit difficult to see. But it's a similar shape in some ways. We have our main sequence down here where the sun currently is. It's at that point with a log luminosity of 0. And then we have a giant branch. So we know eventually some point in the future, our star is going to turn into a red giant. We will all be long gone by then, but that's the ultimate fate of our star. And so with this, we can go back to that question that I asked at the beginning. How do we study stars? Well, we make observations, we make guesses about what those observations say about physics. We translate that physics into math. We use computers to help do the math, and there we go. Now we know how stars work. We just run a bunch of different models for a bunch of different kinds of stars. We compare them to observations, and now we know how stars work. Except if we go back to these equations here, the equations of stellar structure, there's a lot going on behind the scenes of these equations. There's a lot of assumptions and a lot of complexities that get hidden in our path to getting these equations out. So just to name some of those complexities, we've got questions about energy generation rates. Where does that energy come from? What do the nuclear processes look like that lead to that? What about mass loss? Some material must float away from the star. We see that from our own sun with things like solar flares. Rotation, stars are spinning. There is angular momentum there. How does that affect the evolution? What about diffusion? Materials that get moved around and change the composition in different time scales. Non-spherical stars, all of those equations assume a spherical star, but if we've got rotating gas, we know that it's not exactly a sphere. Equations of state, right? We say it's an ideal gas. How valid is that approximation? What does the interaction between matter and radiation look like? And many, many, many more. So the next step in this question of how do we understand stars is that we realize that there are way too many complexities for any one person to be able to understand everything, to be able to work on every piece. So instead we divide it up. Everybody picks a niche and tweaks the models in that particular area. So for today, for the work that I've done, we're going to be talking about this interaction between matter and radiation. So specifically, we're talking about opacity. So if we go back to that equation of radiative transport and we look at this kappa value here, it becomes important to kind of understand what that kappa value is. And so that's the opacity. It is a measure of how transparent the material of a star is to light. So to make sense of this, let's look at a diagram here. If you have a photon that's created by a nuclear process in the core, that photon has some energy. And if it moves out of the star, it's going to take that energy with us. But if it stays trapped in the inner layers of the star, then that energy will stay there. And the opacity can depend on lots of things. The way that I like to think about that and to understand how these factors might change the opacity is to think about a hallway that I am trying to get through and ask the question, well, how easy is it for me to get through the hallway? And the answer to that question is going to depend on, what else is in the hallway and what choices I make sort of in this analogy about moving through them. So the kind of two opposite ends of the spectrum, one would be like, let's say I'm trying to move through a hallway in the physics basement at this particular moment in time. It's not going to take me very long, right? Because many of us are working from home. And even if there is someone that I run into in the hallway, it's probably just going to be a wave, hello, how are you? And we keep going. On the complete opposite end of the spectrum, if you were to stick me in a hallway that was magically filled with a bunch of golden retrievers, I should probably let my roommate know where I am so that she doesn't worry why I'm not home in 24 hours later. And that means, I'm going to stop. I'm going to interact far more with the dogs in the hallway than maybe another professor. Sad to say, but true. And we can think that that same line of thinking would apply to a photon leaving a star. But it's important to understand what are the sources that might cause opacity. So what are the physical processes that could happen that would prevent a photon from getting from wherever it is to outside of the star? And we have a variety of these sources. First and foremost, we have a whole bunch of free electrons floating around in a star. There's a whole bunch of ions and the electrons that are free. And so the photon can scatter off of them, can glance off. Now it's heading in a different direction, not necessarily on its way out of the star. But we can also have free transitions. So those electrons that are moving around, not bound to an atom, can not just scatter a photon, but can absorb it and change the energy level. So that's another process that would, in effect, get in the way of the photon. It's not just those free electrons that can cause opacity. We can also have opacity that comes from atomic sources. So this would be the case of bound free transition of a photon coming in, being absorbed by an electron in an atom, and the energy being high enough that that electron then gets kicked out, fully ionized. Now it's floating free. The other thing that can happen if the wavelength of light is at the correct value, we can get a bound transition. So instead of that atomic electron absorbing the photon and getting kicked off to be free, it just gets raised up to a different state. So that would be, atomic sources. If you are in a point in the star where the temperature is low enough, you can have not only atomic sources, but also molecular sources. And this really is the complexity of calculating low temperature opacities. In atoms, we can figure out the different energy levels of an electron. It gets complicated, especially if you're talking about an atom that has more than one electron. But with molecules, there's an entirely different problem, which is the rotational and vibrational states of the molecule. And there can be a whole bunch of those. And in order to understand the opacity accurately, we have to understand every possible transition between those states. To give a sense of scale for this, last summer I worked on adding methane data to the opacity code. And that involved doing calculations using a transition line list that from one source had 9.8 billion transitions, which is a whole bunch. And while each individual transition on that list might not be super strong, summed up all together, it becomes a really significant source of opacity. It's also worth noting that that list that I was using last summer only has enough transitions to take you up to 1500 Kelvin. If you want to keep going up in temperature, the number of transitions goes up to the point where when you hit 2000 Kelvin, there are 34 billion transitions, and the research collaboration making the line list had to find a new way to get the data out because it just ends up being so much information. So that really is the complexity of low temperature opacity. Anybody who knows a little bit about atomic or molecular physics will note that those transitions that we're talking about, the bound transitions and the transitions between molecular vibration and rotation states, are dependent on the wavelength of light. They're only going to happen if a particular value, particular frequency or wavelength of light comes in and matches that transition. And so this adds an added level of complexity where our opacity is dependent now, not just on the properties of the star, not just on the temperature, the density, the composition, but also on the wavelength of light that we are talking about. And that is one complexity too much for our equations. And so instead of using frequency dependent opacities stellar modeling programs use average opacities. There's a couple of different ways to find an average opacity. And today we're specifically talking about the Rosseland mean opacity. So there is the lovely formula. We see that it's a harmonic mean. So the opacity that we are averaging over gets weighted not with the black body function, that B sub nu, but with the derivative of that black body function with respect to temperature. And what this does is it weights the frequencies with the lowest opacity. And the reason that that matters to stellar modeling is it lets us talk about the areas where the most radiation transfer occurs. What this means is that Rosseland mean opacities get used for stellar interiors. So those are places where we have a black body distribution of photons. This mean value works well. When you get into the outer layers of a star, the Rosseland mean starts to work less well, and we have to use a different mean opacity, typically the Planck mean opacity at that point. But we're talking about stellar interiors today, so we're talking about the Rosseland mean opacity. So if we go back to MESA, that stellar modeling program that I mentioned earlier, the question is, how does MESA find opacities? And the answer is it uses tables. If we look back at the equation, that integral there to find our mean opacity, it is not the nicest thing. So yes, we are simplifying by using a mean opacity, but that still ends up being a huge computational load. And so to make things run faster, folks who write opacity codes will write the code and then generate a set of tables and then pass those tables on to MESA. And it really is because they're quick. It's a fast way to find the opacity. MESA specifically breaks it up into high temperature and low temperature regimes. And that is because the complexities of calculating opacity when you're talking about really high temperatures are different than really low temperatures. So most opacity codes will be bounded in some way as far as what temperatures they are valid for. And this is a figure out of the first MESA paper that kind of shows what areas get each table used for. So we can see, up in the top, we have Compton. That can actually be analytically calculated. Here in the middle, the Opacity project and the Opal project have tables for that area. And then down here at the bottom, we have our very own Dr. Ferguson's tables that get used for low temperature values. And you'll notice there's a couple areas there where MESA has to blend between different tables just to keep things smooth and well behaved. So to understand where opacity differences might matter in stellar evolution, I have a plot here of 3 different stars. All of these stars are the same mass as our sun, but what is different between these 3 stars is the initial composition or the metallicity. And it's important to note at this point that when astronomers are talking about metals, they're not using the chemist's definition of metals. To an astronomer, a metal is anything that isn't hydrogen or helium. So heavier elements than just hydrogen and helium. And here we have 3 stars. The orange star is the lowest metallicity. And so this star would be something that formed a generation before our sun, when there were less metals that had been thrown into the universe by stellar death. The green line is our solar composition, so something similar to our own sun. And then the blue line is a slightly higher metallicity, so a sun that formed with a few more metals floating around. And while changing composition in this way will change some of the other properties in the star, one of the main things that it changes is the opacity. And so that really is the kind of core of this, to understand that composition affects opacity, which in turn can make a pretty drastic difference to where on the HR diagram the star ends up. The early star that we see here in orange ends up, despite the fact that it's the same mass as our sun, being significantly brighter and significantly hotter than our own sun. And so this question here then becomes, is it valid to use the tables the way that MESA is using them? And specifically, if we look at low temperatures here, this is a plot of opacity calculated for a star slightly less dense than our sun. and what the opacity does as you change the metallicity. And as you can see, for higher temperatures, it matters a little bit, but it's not a significant change to change the composition. But as you get into lower temperatures, a log T of 3.7, it starts to diverge pretty wildly. And that opacity gets fairly sensitive to what composition is present. And so these are places where variance in composition leads to significant opacity change. And why that matters is if we go back to the tables that MESA is using, you can't pass MESA a table with every possible value that will ever be encountered in a star ever. Every combination of temperature, density, and composition. It's just far too detailed a table. And so instead, you pick a spacing that makes some reasonable sense, and MESA interpolates. So if it runs up against a point in a star where it doesn't have the exact data for what the opacity is, it can use techniques to use the data around it, fill in the gaps. The question then becomes is, how much does that value interpolated from the tables differ from the actual opacity? And this plot suggests that maybe at higher temperatures, it doesn't matter. But if we get to lower temperatures and we have a slight difference in composition, that's the actual composition, if that's even, slightly different from the composition that was used to make that part of the tables, then it might matter, and it might start introducing some form of error into our models. So the question that I set out to answer over the summer was, how much does it matter that we are using opacity that's been pre-computed into tables instead of calculating the exact opacity every single time on the fly? To answer this question, there were kind of 3 steps to the process. Step 1, have a working opacity code that gives you reasonable answers. Step 2, make that code run as fast as possible. And step 3, plug that code into MESA and see what happens. All right, step 1, update ATOP. So ATOP is the Atlas Opacity Program. It is one of 2 opacity programs maintained at Wichita State. It is the older of the 2 codes, but its main advantage is it is fast. In some ways, it being an older code means that there was less room for error for inefficient coding. Everything kind of had to be pretty optimized to run when it was written for less powerful computers. And that is kind of why ATOP is the code that gets used for this program, because as you will see at the end of the talk, you want something running as fast as possible, because otherwise it's going to be a long, long wait to get out models. However, ATOP being an old code, there needed to be some updating work done, mainly in terms of what kind of compositions ATOP can handle. Originally, it was designed to only handle places where there's more oxygen present than carbon. However, in the last couple of years, it's been updated by adding some more data about molecular transitions. Almost all of that work was done by Kari Arman, who graduated in 2018. I finished the last piece of that puzzle with methane last summer. So now that we can handle with ATOP carbon-rich abundances as well. It's important to note that some of the data in ATOP is temperature limited. And so this code as it stands right now is not something we would want to use to calculate opacities in places cooler than 1000 Kelvin. Which fortunately there's not very many stars where you end up with that low of a temperature. So ATOP is a pretty good candidate for this. It's fast, it's valid over the temperature range that we are interested in, and it's got a whole bunch of recent molecular data in it. Step 2 is make the code run as fast as possible, which in this case means getting ATOP to run in parallel. That was done using OpenMP, which is an open source library of commands to help run a code in parallel. The nice thing about OpenMP is it's the same way that MESA is parallelized. And so when the time came to plug those 2 together, that piece at least played nicely together. At this point, it's important for me to say a thank you to my brother who knows more computer science than I did. and who was very gracious in answering my phone calls and answering questions through this process. I don't know that I would have been able to get through this without his help. So we have ATOP running in parallel. Well, what does that mean? To get a sense of what kind of a difference this makes, we ran a sample grid of 117 points, and running ATOP just in serial, kind of the way it was originally written, those 117 points took 37 seconds. When those points got split across 2 threads, the code finished in 22 seconds. And then when it was split across 8 threads, we finished in 12 seconds. So it's not linear scaling, which is probably to be expected, but it does make a difference. As for why it matters so much to save that, 25 seconds, it's important to understand the scale that we're working with. So for a 1 solar mass star, it can take, at least 5,500 models to evolve to the stopping point where it becomes a white dwarf and we have to change the physics happening. Each of those models, however, take different trials to get to. If you've worked with analytically solving differential equations, you know that trying to find a model that converges on the first try is not really going to happen. So each of those, 5,500 models can take up to 25 different trial iterations to converge. The model that I'll show at the very end was averaging about maybe 10 or 11 iterations, but it can take more depending on how well behaved and how quickly the model converges. And each of those iterations, of course, has a different number of zones, so chunks within the star that are within the temperature range of ATOP. And so looking through this, we might only save 20 seconds for each iteration, but if we're doing, 11 iterations for several thousand models, those 20 seconds that you save each time become really, really important. All right, so we have a code, we have it running in parallel as fast as possible. Now the challenge is to get MESA and ATOP to talk to each other and play nice. One of the benefits of using MESA is that it was designed to make this process fairly straightforward. It's even in the name, modules for experiment in stellar astrophysics. It's designed to allow users to quickly slot in their own code to say, hey, MESA, that opacity that you calculated is not what I want you to use. I want you to use this opacity here that I calculated. That piece was fairly quick. The problem was that MESA and ATOP track abundances in slightly different ways. So MESA tracks how much of each element is present in each zone in terms of mass fractions, whereas ATOP calculates opacities in terms of the number fraction of each element. This is the kind of problem you might expect an introductory chemistry student to be able to work through. Maybe they're not used to it in the context of a star, but it is similar math. So that's not really the super tricky part. The really tricky part is that MESA only keeps track of the species in its burning net. And so by that, it only keeps track of the elements that you have told it can participate in a nuclear reaction, which in the case of the models we were running, just using the most basic net, was about 8 species. But if you try and calculate the opacity with only those species, it's not going to be wrong, because stars, of course, have more than 8 kinds of elements in them, and we do need to account for some of those other sources. So the way that I worked around that is to assume an initial composition, in this case, the GS98. So this is one of the often used abundances of our sun. So, the metallicity might change, right? The amount of metals change, but the way the metals get split up is the same. So we've got kind of the same proportion of, neon to magnesium, the same proportion of oxygen to uranium. That's what this is done. The problem with that is that the species in the burning net that MESA is tracking are changing, whereas the metals are not. And if we just say, all right, I'm going to take the species that MESA has given me, and I'm going to add in the metals that I know are there, you end up with more than one star's worth of material, which is a problem. So there's a little bit of renormalizing the abundances to make sure we're only accounting for one star's worth of material. So with that done, there was kind of one other step that needed to be done to integrate ATOP into MESA, and that is finding a couple of partial derivatives of the opacity with respect to temperature and density. I am sure that there is a way to do this within ATOP itself to kind of track down where the opacity comes from, go back to the analytic forms, take a derivative there and get it out. That was going to be a little bit too much work to finish over the summer. So instead, we're just doing a simple finite difference, which has the unfortunate effect of really slowing down the code. So if we're thinking about next steps, this is definitely something to look into to optimize it a little bit. All right, so now we have a code that's running fast, that's plugged into MESA. The question is, how does the on-the-fly opacity compare to the table opacity? And rather than just running one model and waiting a week for it to finish, it makes sense to kind of be intelligent and be smart about what models we choose to evolve all the way through. So the plots that we're going to see in the next couple of slides are out of sort of a sandbox where we have models of a star at different points in its evolution. And we just say, all right, at this point, if I was to compute opacity of the star off of a table and on the fly, what does that look like? So we've got a couple of different stars here, 3 different stars, the same 3 that we were looking at before, all one solar mass, but with slightly different metallicities. And we're going to look at each of them at different points in its evolution, trying to understand maybe, it matters more if we're using on-the-fly opacities at one point in time or at one point on the HR diagram than on another. So lots of plots going on here. Let's take a moment and explain what's happening. The plot on the left is just an HR diagram for reference so that we can see where in the evolution this profile that we're looking at comes from. So this is a star with solar composition, and the yellow star there on that plot tells us that we took the conditions at that point and plugged those in to our opacity code. So this is on the main sequence. It's the point in the lifetime that our sun is right now. And if we look at the plots on the right-hand side, the one on top gives us our log opacity at the temperatures where ATOP is being used. The red line is the values that MESA would calculate on its own by reading off of a table. And that dark black line is the on-the-fly opacity. So the one that we calculate doing it with the exact conditions at any given point. And because those lines are pretty close together, underneath that there is a difference plot. So this is the difference in log space between the 2 values on the fly and off of the table. And we can kind of see for this point for solar composition on the main sequence, it's not a huge difference to use the tables versus to use the on the fly. It does start to matter a little bit more at lower temperatures, which is a trend that we can kind of see if we step this star forward in time. So now instead of looking at a sun-like star on the main sequence, we're looking in some ways, into the future, what our sun will be like when it is at the very beginning of the red giant branch. And again, not a huge difference between the table and the on-the-fly value. But there in the last few layers of the star where it's at the coolest temperatures, it does start to be different, starts to be noticeable on that top graph that our 2 lines are diverging. Let's continue the trend, step it forward in time. So now we are a little bit later on the red giant branch. And, there's lots of analysis still to be done in figuring out why this difference happens the way that it does. I have not quite gotten to that point, but it's interesting to know what the temperature is that causes the largest difference. That's definitely a question I still have, something that I still want to look into more. So we have a sun-like star with solar composition. What happens if we look at a different composition? So in this case, let's look at that high metallicity. So a star that formed with a little more metals in it initially. So again, on the main sequence, it seems to be that, the lower temperatures matter more, which is kind of what we would expect. But that split is a little bit bigger, even right out the gate here on this difference of composition. If we step it forward, again, that same trend where it matters more using the tables versus on the fly at lower temperatures, and then stepping it forward one more time, so we're late on the red giant branch. Again, that same kind of trend where the temperature has a point where there's kind of like maximum divergence and then they start to come together at the end. But it is a bigger difference here. It matters more in a star with a different composition than solar composition. So what if instead of slightly tweaking the composition, slightly increasing the metals, we take a look at that last star? So this would be the one on the plot where we had the three of them that was completely different. The star a generation before our sun, looking at a low metallicity star. We can see already that the temperature range that we're talking about on the main sequence is a little bit warmer than our sun. Sort of have, again, the same trend of it really doesn't matter until you get to the lower temperatures. Stepping it forward in time again, trend sort of continues, but the most interesting graph for this star is here when we're talking about later on the red giant branch, when it really starts to matter. And I would love to know why it starts to matter so much at this point in time. There are going to be lots more runs and lots more plots through this to try and understand what's going on here. But this ends up being a pretty significant difference between the table value and the on-the-fly value. So that's all interesting. It raises lots of questions about why these differences are happening the way that they are and why they're happening at the temperature points that they are. But it doesn't really answer the question of how does it change the evolution of the star? So over time, what happens if we evolve it using an on the fly instead of off the tables? So that would be what this graph is showing. We've got in red, the star that was evolved using ATOP on the fly for low temperatures. So again, temperatures that are less than 10,000 Kelvin, and compare that to the tables value. And it's not a significant difference. It's not really a difference at all on the main sequence until you get out to late on the red giant branch. But for the sake of comparison, for trying to understand how much of a difference this is, I want to add one more line to this plot, which is this yellow line. So that line is a star that's been evolved using tables out of the Phoenix code. So this is a completely different opacity code from ATOP. Still using tables, but it has different physics used to calculate the opacity. So the question is the difference between using on-the-fly values and table values, how does that compare to using just completely different tables? And I'll be honest, this is not as big of a difference as I was expecting. This model really just finished running today, so I have not had a chance to actually dig in and understand what it is that's driving these differences. But it is interesting to note that it's about on the same order of change as using different physics. So there's going to be lots of questions to answer about that going forward. But overall, using the on-the-fly opacity values has a slight difference on the table values, but this is just one star with solar metallicity. It is kind of the starting model that works the best that comes in built to MESA. So there is a good chance that there are other stars with other properties where it will make much more of a difference to use an on-the-fly opacity versus using one off of tables. So some of these things to try might be, as we looked at before, using different compositions, seeing if there's a point where the composition that gets calculated from tables ends up being completely different from what's actually going on in the star, but also cases that have a more complicated burning net. So MESA is tracking more than just the bare bones nuclear reactions you need to get a star to evolve. That would lead to more complicated changes in composition and therefore perhaps more complicated changes in opacity. It might also matter more for lower mass stars. Those are places where the temperature is going to be lower. So if we're talking about looking at low temperature opacities, a change to that is going to, has the possibility to have a more drastic change in stars where there's more of the star that's in those low temperatures. And then kind of the last one, complete opposite end of the spectrum, looking at really big, really old stars. So population 3, this is an unfortunate naming convention, are the first stars in the universe, the ones that, formed first and therefore were almost entirely hydrogen, helium, a little bit of lithium, but there weren't the metals present in them that there are present in later stars. And there are some lingering questions about mass loss in those stars. So it might be worth looking into, well, is that coming from opacity difference? Is it something about the way that our modeling programs are calculating opacity off of the tables? There's also the chance that these opacity differences could matter in variable stars because we know of some opacity changes that cause pulsations. Typically those are atomic, but there might be something about molecules in there. Lots of questions, lots of different kinds of stars to look at and think about. And even beyond that, what are the next steps of this research? Models of more interesting cases, first and foremost, trying to understand what's driving the difference between the table values and the on-the-fly values. Comparison to observation. So once we have enough models of interesting cases, going ahead and comparing those to what we see in the night sky, seeing if maybe, does this change to the opacity make things match observations more, make observations make it match observations worse, those kinds of things. As far as ATOP, there are a couple of improvements that could definitely be made. First and foremost, speed. So a sense of scale. The model of the one solar mass star solar composition that we were just looking at, when calculated using table opacities, took about a half an hour to run. The one that was calculating with on-the-fly opacities has taken over a week to run. And so any kind of improvement to the speed is going to become really important and compound, especially if we end up into more complicated cases. As well as, of course, there's always work to be done extending the temperature range of ATOP. Would it be possible to extend ATOP low enough that it could be useful for planetary atmospheres? That's kind of a lingering question with the code. So returning again to this question that we asked at the beginning of the talk, how do we study the stars? Well, we make observations of what we can see and what we can measure about the world. We try to understand and explain those and translate that explanation into math. And hopefully we can then pass that math along to computers to help us out. At that point, it becomes really complex. So scientists divide and tinker, everybody picking their area to make changes in and see what happens. Then we all come back together, refine models, talk to each other, figure out what's driving it. In short, we do science. And so with that, I have a couple of thank yous here at the end of the talk. First, to the Evelyn Shaw family for their generous support both last summer and this summer. I also a huge thank you to the Bill Simon Fund who helped purchase the computer Red Giant that handled all of these really intensive modeling calculations. Of course, a thank you as always to Dr. Ferguson for answering my questions, some of them intelligent, some of them less so, but always very helpful. And so with that, I would welcome any questions that you all have.
All right, thank you, Lynn. While Lynn gets a drink of water and catches her breath, next week's seminar on October 7th will be Antimatter-Based Propulsion by Dr. Gerald Jackson, who's a NASA fellow and also works at a company called CSO H-Bar Technologies. So that's next week's seminar. Anyone have any questions?
Yeah, comparison with observations is the big one, right? You want to, after all, validate your model. So what specific observations might you be able to compare to? And how directly does it confirm or refute a particular model, or are there too many other inputs to be able to pinpoint it to the variation between opacities?
I think that's probably going to come down to which specific case that you're talking about. So my understanding of how that comparison to observation typically works is you run a whole bunch of models, and then models based on conditions that we know about, of stars that we know about, and then kind of look and see how well the evolution that comes out of our stellar models matches the stars that we see in the night sky. So looking at HR diagrams of clusters of stars and trying to fit and to understand those differences. I think this particular project is a ways off from being at the point where we can do that. There's still a lot of questions about how the code is playing with each other that I think we need to answer first.
Thank you.
I have a quick question, Lynn, if I may, and great talk, by the way, congratulations. Do you think the discrepancies you're seeing is a result of the lack of actual atomic or molecular data, or is it in the technique of the calculation that is generating a difference? Is there, and it's kind of a two-pronged question, is there an application of kind of advanced machine learning or AI? There's a very strong computer science section at Wichita State, which I've been chatting to a little bit about machine learning. I'm wondering if there's an application here.
So to the first part of the question, the differences are probably not due to like atomic molecular data, because the code that generated those table values is the same kind of version of the code that we're using on the fly. My suspicion at this point is that those might be due to how we're renormalizing the metals and accounting for that. So that's definitely like an open question I have as far as how accurate that renormalization is, what it looks like. And then as far as machine learning, I honestly don't know. That's not something that I have a ton of familiarity with. But, you know, I think that that's a technology that's going to be showing up in physics research more and more. So it's definitely something to keep in mind.
Just to let everyone know, you know, during the summer, of course, it was a little difficult since we had the COVID protocols and we couldn't be on campus. So we were, Lynn was working from home, I was working from home, and we were trying to communicate as best we can. And so the idea was to take this old 1980s Fortran code and get it to play nice with a modern code. In one respect, it's kind of a computational science exercise. And, you know, Lynn didn't really have time to go into the and I don't think anybody want to know the nitty gritty details of how they got them, how the got them to play with each other and how to parallelize it, because that was the thing that was most interesting, was to parallelize the code. And you know, the fact that even happened, I was shocked at, because when you take a 1980s Fortran code and you use OpenMP on it and it actually works, I mean, that's kind of amazing. And so there was a lot of time that was spent trying to figure out how this works, how that works, and is this the right answer? And I'm really glad of your answer to Martin's question, Lynn, because it showed you had suspicions of your own code. I don't believe this thing right now. And that's kind of where we're at right now. We're not really at the point where we can go, you know, model 47 Took and try to, you know, figure out, yes, this is a better answer than that, or something. So it was really a nice little study project, but it's a lot of hair has been torn out, and there's been some real complications. Any other questions?
Yeah, I have a question, Jason. Dilemma. Did I understand right? The main computation in this code is solving that system of differential equations?
So that would be the main computation in the MESA code. In the ATOP code, it's the integral of the mean opacity is the big code. And also figuring out how much of each molecule is present is the other big computation that ATOP does.
I see, okay.
Yeah, and the equations of stellar structure as shown on the screen were the nice ones that are easy to understand for a 500 level student. The equations that MESA actually solves itself are really parameterized in a mass space, and they're not nice to look at. They are, I mean, obviously, you know that if you take a set of differential equations, you have to turn it into an algorithm somehow. And so it's it's extremely messy, and we're just trying to get our little tiny code to play nice with the big one.
Okay. So any bottleneck in the computations is probably not in the MESA code then.
It's entirely in the ATOP code.
Okay.
Now, Lynn, ATOP does two things. It does equation of state, and it does integration of the opacity. Where's the bottleneck?
That is not a question I know the answer to. Come to think of it.
I'm not sure. I think it's the equation of state. Because the equation of the opacity is just an integral over nu, and it's just you know, integral d nu, and it's you could split that up to 1,000 processors and it'd be easy. But the equation of state is the one that takes I think that's the one that works the hardest.
Is that some kind of data fitting problem?
That piece of the code, to my understanding, is a really complicated matrix, because it's taking data about all of the molecular species and trying to figure out at this temperature, at this density, how much carbon monoxide is going to be present, how much hydrogen is going to be present. And so it ends up being, to my understanding, a pretty messy set of chemistry. And I think it ends up in a big matrix. That is not a part of the code that I dug particularly deep into.
Okay.
Can I ask you a question?
Absolutely, go for it.
I mean, so as you know, I'm in particle physics, and lately I've been thinking about these things called Parton distribution functions. And there's actually a set of partial differential equations that are coupled. And practitioners in this have some serious, you have to create tables just because it takes quite some time to do all the calculations. And I was doing some reading, and then I came across that they had, what they do is they end up transforming the differential equations using some integral transforms to make it a lot easier. And then I also found that they had published some codes that are using GPU systems. So it seems like a lot of people, so they were not doing things on the fly either. They would create these tables and then would use them. Now it seems like, you're kind of doing kind of the similar thing. You want to do on the fly calculations. And I'm just sort of getting into some of that stuff conceptually, like thinking about, well, how could we, because the problem with these tables for PDFs, and it's probably the same way with you, is that these lookup tables soak up a lot of memory on the computer. And this actually slows us down when we want to do scattering calculations. So, I had a colleague at Fermi, he was looking and doing these PDF or these interpolations on the fly. As when we scatter an event, then you would do they call it Parton distribution evolution, but it's basically a differential equation. And instead of looking at going to the tables and interpolating, I don't know what the speed is on the interpolation. I have no idea, but it's an interesting thing to think about, reading all the data and then trying to interpolate versus on the fly. And so I'm curious, and I might ask you some questions about what your ATOP is actually doing, because I'm just kind of curious about what's under the hood. And, if I could help in any way, I'm happy to. So,
yeah, I think the opacity tables that MESA is reading off are not ridiculously large. And so the interpolation happens really quite quickly, which is the main reason for the difference, right, of the same model using table opacities taking, half an hour and using on the fly opacities taking a week.
Okay.
Now, if we could draft a computer science student who's willing to wade through some 80s Fortran code and try and optimize that could be helpful. I certainly think there are probably some computational techniques or using GPUs that might work, but we got the code running in parallel. And so that was a major success of the summer.
Yeah, I'm not saying to look into GPUs. I was just I'm thinking about this stuff a lot now, and I was curious about your specific mathematical problem. What were the differential equations that needed to be solved and stuff. And not that I would rewrite the code. It would just basically, I'm just curious, so maybe Jason would share the papers with me. And
yeah,
if you want.
That would be in the MESA papers for sure.
Okay.
Any other questions?
I'll ask about star composition. You said that composition affects opacity, and you talked about population 3, the oldest stars with the simplest elements, hydrogen, helium, maybe a little lithium. In the progression to population 2 and 1, this might be, I don't know that much about stars, but does it just progress continuously through the periodic table, like the next element and then the next element, and then does that age correspond to opacity then?
So throughout the generations of stars, right, each generation of stars forms from the material around it. The fusion happens in the core, which creates heavier elements. So, hydrogen gets turned into helium, and then that gets turned into carbon, nitrogen, oxygen, magnesium, and it goes on down the line. The really heavy elements come from kind of star death. So, when a star goes supernova or when 2 neutron stars fuse, that's where the really heavy elements on the periodic table come from. So if you have, a massive star, one of the first stars, massive, lots of hydrogen and helium, it burns through that and then explodes. All of that material that had been created, all of that, carbon, nitrogen, oxygen, neon, all of those elements then get scattered throughout space. So the generation of stars that come after it have more of those metals in them from the beginning. And so then because those metals are present, you know, they contribute to the opacity, or they can form molecules that contribute to the opacity. So that's kind of the link there between generation and composition and opacity.
So newer stars more opaque.
I think in general, yes. I am sure that there are some details in there, but more metals tend to give more sources for opacity, higher opacity.
Okay, if I can ask part two, or maybe this counts as the second one, but opacity relates to, you said, the radiative energy transport equation, or matter radiation interact. Does it also affect, or is it calculated with diffusion and some of the other complexities?
So diffusion is actually kind of one of the things where it might be important, again, to have the on-the-fly opacity, because the diffusion would be like the composition would be changing. So that the elements that get fused in the core then get diffused out to the rest of the star. And of course, that's going to change the opacity of the rest of the star. So yeah, all of these complexities are all intertwined and linked, and they all impact each other.
Thank you.
Any other questions or comments? Well, I guess we shall probably end here. A reminder again, next week's seminar is on antimatter-based propulsion, and I appreciate your time and the time you spent with us today. And thank you, Lynn, for all the work you've done last couple summers. And you're available next summer, right?
No.
Oh, you're going to try to graduate. Okay, well, that's fine. Well, thank you again, and we'll see you all next week.
Thank you.
Thank you.
Thank you very much.
Bye.